Hey, hi everyone. So for this video, I'll discuss transient conduction and more specifically, it is outlined with the subtopics. So we will discuss the different um, basics of conduction. No? So we'll discuss the heat conduction equation, and then we will investigate the simplest type of transient conduction, the lump systems, and then we will move with the little bit more complicated type of transient conduction, which are this one dimension transient conduction. So to begin with, let's review what is um, transient conduction. So in transient conduction, basically you have a varying temperature over time compared to the steady state. So to be able to understand how transient conduction works mathematically, we want to review, or actually to understand, no, to be familiar with the mathematical equations involved with heat equation, no, in general. So, for example, you have a material, a body, which is this, no? And what happens is when heat goes from left to right, as you can see, no, during this material, then you will have a flow of heat Q, and then in some cases, no, for example, you have an induction wire, it can also heat, no, or it can generate heat, and then it can also store some heat. So basically, this differential equation right here represents that phenomena. So with this differential equation, after solving this differential equation, you can find what will be the temperature profile of your body with respect to not just the space x, but also with respect to time. So if we solve this, or where did this equation came from really is is this energy balance, no? So if you have again this material and we choose this volume element, or we can control this, we can call this the control volume. So basically you have this volume here, it's like a plate, no? This is three-dimensional um plate. So it has a volume, no? And we can imagine that volume is just the area, no, the cross-sectional area of this, no? So this is the cross-sectional area multiplied by its thickness, which is this, which is delta x. So if we utilize the energy balance, as we can see, as heat goes from left to right, you have Q here, Q sub x flowing to the right or into this control volume. No, you can think of control volume as an infinitesimal, no, or a very small volume. So what goes in is Qx, so it is positive. What goes out of the volume element is negative. So you have Qx or Q sub x plus delta x, no? And then you have some heat generation within the element if you have, no, depending on what type of material it is. If it is electrical, usually it can also generate heat in by its own, no? So it can generate heat on its own. So you have plus heat generation. Now, some of the energy will be stored, no, within this element, no? So you can imagine like a pan, no? So a pan can store energy and then disperse it later on, no? So basically, this is just what goes in, what goes out, what goes in, and then this is equal to the energy stored. So I won't get into too much details here, but the some of this can be simplified, no? So the energy stored in an element is basically just mc delta t, no, or mcp delta t. So the heat generated by the element is can also be written as this. So this is the heat generation flux, and usually this is in watt per cubic meter, no? For example, for SI. So therefore, you can multiply that by its volume to get the energy, no? So if you simplify this, you can have this form, right? I forgot to mention your mass is also equal to volume, no? Times volume that times the density. So the volume can be represented as the area, the cross-sectional area times the height. So you have A delta X for the volume and multiplied by rho, no? Which is the density. So simplifying this, you can actually divide the both sides of the equation with A over delta X, no? Okay, so to simplify this, you can divide everything by area and delta X, and you will have this equation, no? So an additional manipulation, as you can see, this will become negative because we swap the signs to this. So basically, we just factor out -1. So this will become positive, this will become negative. Okay, so the reason behind that is that because this looks familiar, right? Okay, so this looks familiar. This looks like a derivative. So the definition of a derivative, you have a numerical derivative, but as delta x approaches 0, what happens is you have an actual derivative, no, a continuous derivative or an analytical derivative. So you can rewrite this into this. So we can also transform everything instead of delta t. We can say that this is the change in t, no, the dt. Or if this is a partial derivative, we can say partial derivative with respect to say for example time for this one, no. So again, we can change this one. This is basically just this, no? So we can write this as negative k del t over del x. And then we can cancel out the area here, as you can see. So what remains is just k and del t over del x. So what happens is you have this, and then everything will just follow. So this will become del t over del time, or del temperature over del time, since this is a function of time, no? This is a function of x, no? Okay, so that's basically how it is derived, and depending on the scenario, we have different cases, and usually we're only studying the simplest cases, no? So for steady state, you have this with heat generation, no? So steady state with heat generation will be this equation. For transient, no, with no heat generation, you have this differential equation. And for steady state with no heat generation, you have this. So what we've studied so far is just steady state with no heat generation. So if you might ask, why is this? What is the meaning of this? Why is this important? So I just want to show you that the transient differential equation is much harder or much more complicated than the steady state um, differential equation. No? So for steady state with no heat generation, the differential equation is just the second derivative of time, or sorry, of temperature with respect to the space variable x is equal to 0. So what basically means is that your slope, no, is just a constant. So because if you find the derivative of this, then this will be 0. No? So basically, the profile of the temperature with respect to the space variable is linear. No? As we can see before, when I've drawn the heat conduction to a wall, it is just a line. No? The temperature profile is just a line. Meanwhile, with this one, it is much more complicated, and this is harder to solve compared to the steady state. No? So, just to give an idea, what this means is that the temperature has a dependency on both the space variable and the temperature. No? And they have a relationship between each other. That's basically the simplest way to explain that. Now, again, just like what I've said, transient heat conduction or transient heat transfer problems, the temperature varies with time. So if you have a steady state, you have 15 and 7. After a while, it's still the same temperature. No? So that is steady. No? So the heat flow will be consistent as well because the temperature is not changing. Although in reality, well, sometimes we can assume that it is a steady state if the temperature difference is negligible, no? The change in temperature here or here is negligible, but in real cases, as we can see, the temperature will vary over time. So after, let's say, 3 hours, the temperature of, let's say, the inner and outside walls will be different after that time. So in transient heat conduction problems, the formulation is much more complicated, no? And in addition to this, going back to this wall, the heat transfer is not also constant, no? Because the temperature is changing. So you have 15 minus 7. Actually, this is still, no. Okay, it is different really, yeah. In this case, this is still different because this is 15 minus 7, 8, and then 12 minus 5 is 7. So you will have a different um, heat, no? On 2 p.m. and 5 p.m. for heat transfer. So both problems still has a profile of change in temperature with respect to the space variable over time. Not over time, but with respect to the space variable only. So for this case, the graph is just like this. But for transient, it might be different, no? But we can maybe imagine it might look something like maybe like this, something like a wave function. And then after a while, it will be something like this, no? So it is not that linear anymore because, again, steady state, usually it is just linear and consistent. But anyways, let's move on and let's discuss the one that is more important. How do we solve these transient conduction problems? So another important concept is understanding that if you have a body, if you have an object, then the temperature within that object will vary within itself. No? So you can imagine a copper ball, no? Since it is highly conductive, we can imagine the temperature profile of copper ball is uniform. No? Compare that to meat or roast beef in this example. If you try to cook roast beef, let's say in 30 minutes in an oven, so you might notice that the surface of this beef will be high, but within the meat, no, the temperature might still be lower, no, than the surface. So, in understanding transient conduction, we have to really begin with the simple one. So we are assuming, no, in the lump system analysis, that the body is uniform in temperature. So this is the simplest type of transient conduction, no? So if this is the case, then we can use a very simple approximation to find the heat transfer rate of this, let's say that this copper ball within this environment, no, within, let's say, the air. So again, it is uniform in temperature. So this is the lump system. This is the not lump system. Another thing to take note of is that lump systems or this lump parameter model, no, sometimes we call that is that this is a zero dimension, no? Zero dimension model, no? So why is that zero dimension? Because we can imagine instead of this very big circle here, since the temperature is uniform, we can imagine that's just a point, no? You can imagine this as a point that is just 70 degrees. So it doesn't have an x or y coordinate. The temperature is just 70 degrees Celsius, so it is zero dimension, no? So it definitely simplifies the transient conduction problem. Now, if we use an energy balance for a lump system, a lump mass, a lump body, with a very simple scenario wherein you have a surrounding fluid, no? And we experience conduction, or the body experience convection pala, no, not conduction. So as you can see, if we do this heat balance, the body can absorb heat from its surrounding or also expel. And if it, for example, absorbs the heat, no, in terms of the convective heat transfer, then it will store this energy within it. So the temperature will also increase. So we can represent that as this equation using this energy balance. So the heat through convection and then the energy stored. So if we simplify this, actually this should have a dt, no, in here. So if we solve this, no, you can see this is a differential equation. We can do a separation of variables. So we have t here, so this should be on the right hand side, and that t can stay where it is, no. So you have HAS dt is equal to MCP dt over you have t infinity minus t. Now, what we can do now, we can change this one if you want. So instead of CP, sorry, not CP, but the mass. Instead of mass, we can say this is rho times the volume, no? So the mass is also the density times the volume. And then for this one, we can swap this, no? So that the it is much more easier to differentiate. So what happens is you have negative rho v and then Cp and then dt over t minus t infinity. So we just swap the signs. We factor out the negative. Okay, now integrating this both sides, right? So we're assuming that the heat transfer coefficient is also constant, no? And then the area is constant, density is constant, volume is constant, rho is constant. So if we integrate this, we are just integrating the variables here. So the temperature will vary. That's it, no? So if you do the integration, we have to also include the limit. So the limit here will be for time. We start with t is equal to 0, and we end with t is equal to, let's say, well, the time, no? And then for the temperature, we start with the initial temperature, and then we end with, let's say, just temperature, or whatever temperature it is. So if we simplify this integral, we have HAS, and then you have t, evaluated from 0 to t, and then equals to negative rho v Cp, and then this will be, so we can use, what is the integral of this? This is integral natural log of t minus t infinity, and then evaluated from, actually I can just write this here, from ti to t. So simplifying this, no, you have HAS, so you have t here, and then this one, so you have negative rho v Cp, and then ln of t minus t infinity all over t, sorry, not over really, no, but we will simplify this later, no? Infinity, and then you have minus ln of ti. So we substitute the ti, no, and the t, and then t infinity. So as you can see, we can simplify this, no? So you can say that this is negative rho c, and then you have ln of t minus t infinity all over ti, and t infinity. Okay? And then you have HAST. Okay, so we want to solve for the temperature here because this is what we are, I mean, that is the function, right? So this is a function of temperature and time. So we will represent this as a function of t. So what you can do is you can write this as HAS t, and then divide this by negative rho v. So you have negative here, rho v Cp. Actually, I'll factor out the t here, and then equals to natural log of t minus t infinity over ti minus t infinity. So if you use the exponential function, so we use the exponential function for both of this, or the natural log. So what happens is this will become t minus t infinity all over t minus t infinity, and then equals to e. So to make things much more compact, we can say that this is just b, no? So negative b and then t. So this is where it starts, no? So you can find the temperature, no, t, okay, as long as you know the temperature of the environment, the initial temperature of the body, the time, the current time, and also the other parameters here: the convective coefficient, the area, the rho, the density, the volume, and the specific heat capacity. Okay, so if this, I hope this looks familiar because this is just Newton's law of cooling, basically. Okay, Newton's law of cooling lang yan. So, we can find the temperature and the heat flow. So the heat flow will vary over time, no? Depending on the current time, the temperature will vary. And as you can imagine, no, that the temperature will originally be, or the temperature difference will be high, meaning the maximum heat will be around the initial temperature, no? Okay, and then you can also, let's say, imagine you can vary the convective coefficient, meaning you can try forced convection versus natural convection, no? So you can increase H by increasing fluid flow, right? So if you increase the fluid flow, so comparing the different B here, oh, so if you increase the fluid flow, what happens is the temperature of the body will get closer much faster to the temperature of the surrounding compared if the B is lower, no? Okay. So again, no, you can imagine that the heat transfer rate will be much higher for for the initial case, no? So if you have a very hot coffee, you can imagine you have, let's say, a coffee that is, let's say, 80 degrees Celsius, and then the surrounding is 24 degrees Celsius. So the maximum heat transfer will occur when the highest temperature difference is present, no? But after a while, what happens is the coffee will cool down into, let's say, 40 degrees Celsius. So the temperature of the surrounding is still 24. So as you can see, the heat will go lower. So usually the initial temperature is the highest heat transfer rate, no? No? Where T is equal to 0, or the time is equal to 0. Okay? So I hope this is clear. So we understood, no, that we have a mathematical model for representing the temperature and the heat flow for a transient, no, case, no? But when is that applicable, no? How can we say that this analysis, no, this formula, this two formula that we are using, how applicable is this, no? So this is only applicable for uniform temperatures, right? So there is a measure of how a body is kind of uniform in temperature, no? We call this the lamp or the criteria for lamp system analysis. So we can find the Biot number, BI, and if the Biot number is less than or equal to zero point 0.1, then we can use the lamp system analysis, the formula that we've shown, no? So the Biot number is basically just the ratio between the convection, heat transfer, versus the heat conduction within the object. So as you can imagine, this will be just, this is the same as you have H delta T over K over L, and then delta T, no? So this is just convection, right? And this is conduction. So you can cancel the delta T. You can see this is just HL over K. So you might ask, what is L? No? So L here is the characteristic length, no? And that is just the ratio between the volume of the object and its surface area exposed to this environment. No? Okay, so again, we are the formula in the previous pages is only applicable when the byte number is less than 0.1. So you have to compute the byte number first before you can utilize the formula given in the previous slides. Okay, so for the next video, I'll discuss the illustrative problems.